my screen.
So we are very happy that you are willing to give a plenary, let's say, presentation today about your work you have done. So you started your PhD here in Braunschweig at my institute, something around 2003, I guess, or 2004, when Jörg Schwiedes was still the head of the institute, and then I took over in 2005, and in 2009 you then finished your PhD with the theme on stirred media milling of nanoparticles in aqueous and especially non-aqueous media. And afterwards, you know, you have been working still at my institute as a working group leader, and especially also worked on we call it stress model, which I started to define during my PhD and afterwards. And I think you did a great work, you know, to bring it to a, let's say, new status, how to predict really the optimum parameters and also the specific energy consumption for at least stirred media mills from, let's say, basic data, not without any experiment. And maybe we heard here today about that, I guess. And so we are really looking forward to your presentation. And maybe I can say that she is now really just on the jump, I would say, to another position. So she got a professorship at the University of Applied Science in Nuremberg. So it's the Institute of Ulrich Teipel, maybe some heard about him, who's working in a lot of recycling of materials and also mineral processing. And so she will, let's say, proceed her career then now in another university. And I wish you a lot of luck there, Sandra, but we talked about that already. And now a lot of luck for your presentation, and we are looking forward to that.
Okay. So yeah, many thanks, Arno. Then I start now to share my screens. I think this should be the right one. Okay, can you see it?
That's good. Yeah, perfect.
Yeah, okay. So I go back here and then I put on the presenter. And then, yeah, very nice to be here. And I would like to thank you for your introduction and also for the invitation to have a lecture here today. I think Arno said most of the historical things about the model. I came from stirred media milling, and I would like to take you today on my journey of the enhancement of the stress model. And I would like to show you at least the opportunities and boundaries. And I was very glad to have 45 minutes, so I can go a little bit more into the details. And I would just get you a part of what I thought, how to improve it, and maybe the things I thought which might work or even not work. But let's start with the motivation. As I said, I did my first steps in scientific work in stirred media milling, and I started with nanoparticles and ceramics, but during my PhD time, I learned rather quickly that there are many, many different products which run at least in one unit operation step in a stirred media milling. There are not only ceramics, there are minerals and ores and pharmaceuticals and life science products like UV blockers for sun cream, or even paints and inks and so on. So there is a broad range of products which can be at least produced in a stirred media mill or have a production step in a stirred media mill. On the other hand, I gave the lessons for the introduction of process engineering. And one of the things we usually tell the students is that 2 to 3% of the global electric energy is consumed by comminution processes. At least these numbers seems to be very small, and they are not really, let's say new. It's older numbers, maybe they have changed a little bit. But when you see it, it's not that you say, okay, it's a lot. But I broke it down to, let's say, explicit numbers just for Germany. And when you have a look that, for example, in Germany, around 500 trillion watt hours of electrical power was consumed in the year of 2014, then you can even estimate how much energy only in Germany was consumed for comminution processes, still 13,000 trillions of watt hours. And I think these values are really impressive. And I don't know how many more zeros will come to these numbers if you look, for example, worldwide or for the US, for example. At least this is where I started, that I thought, okay, comminution processes run sometimes or often maybe not very efficient, and it would be a great job to run them only a little bit better. So if you want to improve it, just let's say by 1%, you would have energy savings only in Germany around 130 billion watt hours. And I guess it's really a lot which can be done there. And so I thought, okay, how can we start with it, or what can we do? And so I started at least, let's say, with the motivation, I want to develop a simplified model, and it should be able to scale wet steered media milling processes. Also, when, for example, the mills are not self-similar. It should be possible to transfer at least these processes from one mill type to another, especially, I guess, in the last 20 years, a lot of different mill geometries came up by the different suppliers, and they all have, let's say, a little bit different characteristics. And at least it should be possible to optimize running processes. And my starting point was the original stress model by Arno. He said at least that colliding grinding beads have a certain energy, a certain kinetic energy, which is proportional to their mass, by sure, and at least to the grinding bead velocity. This grinding bead velocity is usually not available, so we don't know, and we can't measure it in a mill. So the idea was to set it, okay, it's at least somehow proportionate to the stirrer tip speed, which is typical operational parameter in a steered media mill. And so he came up with the stress energy of the grinding beads. And when running experiments, you pretty know, I guess, all know this type of diagram. You see on the y-axis the specific energy for a certain particle size. In this case, it's 1.5 micron. And if you plot this over the stress energy, you get this nice minimum curve. And so it was possible with these curves to find the optimum operation conditions to run the process very energy efficient. But at least one has to say that each data point you see here within the figure is at least connected to minimum one experiment. So you can find out at least the connection between the specific energy and the particle size. On the other hand side, this model in this condition is only possible to optimize at least your process here for exactly this product in this mill. So if you change the product, for example, or the solids concentration, or even the mill, you will get other curves. You will get optimum curves, but they will have not exactly the same numbers or shape like this. And so I moved on. I guess this figure, maybe many of you also saw in a similar way, because this idea to have, let's say, a measuring part of the model and a material part of the model is not new. I guess I saw it in some paper written by Peukert. And I think at least we need a third part in this model, not only the machine and the material part. We also have to have a look, let's say, like on the bulk or the suspension level here. As I talk about now about wet grinding, it's the suspension. So I think also the rheology or the solids content, or maybe the state of agglomeration or sedimentation and steered media milling processes should also be taken into account. Well, for the machine and the material function, I guess it's the typical parameters. For the machine, you have the type and the construction. When you look at steered media milling processes, it's the grinding media size, the stirrer tip speed, the filling ratio, and so on. Usually when you look at the materials, you really look what is the solids, properties like the density, the Young's modulus, or the compression strength. Altogether, bring you at least to two, let's say, significant or important numbers within the stress model. This is the stress intensity and the stress number. And with this in mind, I thought, okay, with these numbers, the stress model should be set up in a way that we can have at least the product properties we would like to have. For example, like in this case where I produced transparent ceramic nanosuspensions. And so at least two different points I would like to talk about. First, I started to talk about how can we predict this energy efficient operations with at least my desire was with no experimental work or even less experimental work. And then I went on. I thought, okay, it's nice to have the optimum parameters, but it would be even nicer to also have an idea how much time I would need to run the process to get this particle size I would like to have, or even to estimate the energy out of it. So let's start with it. What is at least influencing the optimum conditions? So first, my basic idea was to say, okay, I need at least two energy values I can compare somehow. On the one hand side, I need the energy which is really transferred to the product, which is at least a function of the suspension of the process parameter and also on some kind of the product material. And this energy needs to be minimum equal or even a bit higher than the breakage part energy of the particles itself. And so I thought about first, what do I need as machine parameter? I have the process parameters for sure. We talked about them. They are included in the origin stress model. Everything okay. But at least I said, okay, the stress model as it is doesn't recognize at all some geometry parameters. And there are many different geometries of steered media milling. So I thought, okay, I need some idea to put in the geometry parameters. And at least both together deliver somehow a stress energy value by the grinding media. But not only. It's not only the mill which is at least influencing the delivering energy. It's also the material and suspension part. And when we go here first to the second point, because I came from the machine part, we will have some reduction values within our equations, which at least reduce the transferred energy. And these are a function somehow of the deformation behavior of the material and the grinding beads in relation to each other. These are values like how many particles are stressed per stress event, because at least, especially when you go to very fine particles, you can assume that there is more than one particle stressed during a stress event. And at least we have the viscosity, which play maybe a role. So I would like to start first by introducing you what I thought about the geometry parameters, and then I would go on with the material and suspension part. Before I do this, I would first like to show you the different mills you will see within my presentation, just to get an idea how big they are and how they look like. So I will mainly show results of 4 different mills. You will see some more, but they are not in focus today. There are 2 ones in real lab scale, which are LabStar mills. The LabStar you can see here in this figure, the blue machine, and we use 2 different rotor geometries for it. On the one hand side, we have got the zeta geometry, which was developed by Netsch, I guess, at the beginning of the 2000s. Especially for nano grinding applications. You see, it's not the typical discs. It's like let's say something like pins, and you can see here a really these holes in the rotor, which is what's done for the separation of very small grinding beads. This mill has a grinding chamber volume of a little bit more than half a liter, and I used it for many of my experiments, especially for the different materials in nano grinding. And as it was usual, I guess for nano grinding applications, I used zirconia beads because they were said to be very wear resistant and available in very small sizes. Later on, my coworker David, he used the LabStar discus geometry for a certain industrial project. It looks in principle like a disc mill. Maybe it's cannot be seen so good here. And at the end, you have something like a cage, a separation system for the grinding beads. The grinding chamber volume is a little bit higher, and here we used alumina beads because it was something like minerals grinding and much coarser. And then we have an ISA mill available at the Institute, and we were able to use even a bigger ISA mill at Bitossi company. And here 2 master theses were run to grind dolomite, also with alumina beads. And in principle, you can see they look very similar. They are only different in size. They have discs with holes inside, and these pins at the end as separation unit for the grinding beads. Okay. Then let's go on. So first, when I wanted to look at the geometry parameters, I for sure looked up in the literature what is available. And there was a guy who did work on it. It was Hans-Henning Stender. He was working at Mr. Schwede's Institute. And he defined for steered media mills based on fluid flow simulations different areas to assume how the gradients of the grinding media velocities look like. So at least he took the assumption, for example, that at the disk, the grinding beads have the velocity of the disks, and the bigger the distance between the disk and the grinding medium you look like, the velocity decreases with a certain gradient, which was based on fluid flow simulations. And therewith he was able to calculate at least grinding media velocity distributions. And with this, it is possible to calculate the stress energy distribution. And I did this for the 4 mills I showed you before, and you can see the result here. You can see here at least the calculated stress energy in relation to the maximum stress energy, which was the same for all the mills. And when you compare the results with each other, you can see that at least the 3 mills with the discs look very similar. They have a similar geometry, and so do the distributions look very similar. What also can be seen is that the curves are shifted from small grinding media volumes to bigger grinding media volumes to smaller values. The ones for the theta geometry, it looks totally different. So it's a totally different stirrer. And so the distribution looks different. From these curves, I calculated at least the mean values. And okay, does it go on? No, it doesn't. So the slides don't move at the moment. I'm sorry, here's nothing happening at the moment.
So your PowerPoint got frozen, correct?
Yeah, it's frozen, and now he says PowerPoint is not reacting anymore. I'm sorry. Hope it will run soon again. Okay.
Maybe you stop sharing and reshare, and see if that does.
It doesn't react anymore. Okay, I stop sharing. I have to restart it. Maybe it's getting better. I'm really sorry, but that's, I guess, typical PowerPoint. Okay.
Okay, during my presentation, I had a power outage, so I just disappeared completely during mine.
Okay,
recall.
let's see. We were here.
Yeah.
Anyone notice, Malcolm?
No, they didn't seem to.
I did.
I guess we all know this. It happens. Just wait and
Yeah.
start.
It happens to all of us.
Yes.
There, I guess. I hope you have a little time. So I
You're
think
back.
now you can maybe see the slide again. I restarted it
Okay.
and I hope that I can now go on. Here it is. Okay, here we are.
Yeah. Good.
So yeah, here are at least the values I calculated for the mean values here. And here, as you can see, they are pretty different. And it's at least totally clear that these mill have a different, let's say, milling performance when you look at it. And so I included this, I called it a mill-specific factor into the stress energy to recognize at least the mean stress energy and not the maximum one, which would be the same for all the mills if you use the same process parameters. Okay, I think I don't know if you see my, I know it's back. Okay. Okay. Now it stopped again. Okay. Here, and then I would like to come to the next part. I have to slow down maybe a little bit. I'm too fast for my PowerPoint. Where I would like to show you at least what I think about the material and the suspension part, and how I rearranged or enhanced the model with some material parameters. And there I also had the luck to have somebody else who did already some work on it. This was Michael Becker, who was also working for Mr. Schweders, and he introduced at least something like an energy transfer coefficient for the product, which is recognizing the deformation behavior of the product to the grinding beads. And when you introduce it into the stress energy, you would take the reciprocal value. So you can see it here on the y-axis. And I plotted it here over the ratio of the Young's modulus of the product and the grinding beads. And you see if you have a very soft material, like for example, zinc oxide and grind it with zirconia beads, you see that you have got a reduction due to the deformation of the grinding beads in comparison to the feed material of, let's say, a little bit than around 20%, not so much. If you go to materials with are much steeper, like for example, some quartz or some fused corundum, you can see that the curve is decreasing. And especially for the fused corundum, you have reduction values of around 70%. So only 30% of the energy, which is at least provided by the grinding beads or could be provided by the grinding beads, is really transferred to the material due to the different deformation behavior. So here it would be a good, let's say, hint to say, okay, the grinding beads material as possible should be adopted to the material. So if you have got really hard material, it is helpful to use also very, yeah, let's say very steep grinding bead material. Then the second point I had a look at. Okay, now it's not running again. the next point would be the rheology I would like to talk about.
Yeah, perhaps you can do the same we did last time. Just yes, yeah, it appears.
Okay. Yeah. No, it's too much. Okay. Let's not talk about the animation. We leave it like this. Is the viscosity. Here, I thought, okay, if you've got high viscosity, you also have some reduction of the grinding bead velocity itself. But at least I looked at all the experiments I had available, and later on I decided not to take this into account. And here I would like to show you, for example, you see here the viscosity over the shear stress on the x-axis. You can't see, but I'm not trying to make it back here. And what you see here is at least experiments for alumina grinding in the nanometer range. And if you grind it with a pH value of 5, you have a very stable suspension. So when you look at the suspension in a bottle, it looks like a milky fluid flow. It's like aqua, it's very thin flowing. So the viscosity is very low. If you go up with the pH value to 10, you destabilize your suspension. So the particles are starting to agglomerate. And with this agglomeration, usually the viscosity rises. And this can exactly be seen here. Yeah, so the viscosity increases, but only for small shear rates. So if you would look at the suspension in a bottle, it would look like a pudding. And you would say, okay, I think grinding beads won't move that much. But as we know from Newton-Reynolds relations in mills, there are very high shear rates. And for our rheometer, the maximum value was 1,000. And from the back calculation of the Newton-Reynolds diagrams, I came up to values which were roughly 1 or 2 decades higher than this 1,000. And so I decided to neglect the rheology value because I think in the mill itself, it won't play a role. It will play a role within your periphery for sure. If you have got some pipes around, or let's say like a steerer, a steered vessel or something like this, you will see the viscosity and it might have negative influences for sure, but that's not influencing the milling process itself. So this is the reason why I neglected for the things I did here, the energy transfer coefficient of the viscosity. I only took the one of the product into account. Okay, now PowerPoint is not reacting anymore. I think I have to restart it again.
Sandra, can you send that to someone like Sherry and they move the slides ahead so it's not freezing on your computer?
Yeah, I can try it. Okay, now it is. Then I have to stop my presentation now.
It's just a suggestion. Sometimes that works.
Yes, that's definitely a good one. Sherry, are you available to do that, or I can do it myself?
Happy to try.
Okay, thanks.
Okay, then I sent an email. I hope it's not too big.
But maybe in the meantime, you can just try to get back and just in case.
Yeah, I first sent the presentation now, and then I try to restart it.
Thanks.
Yeah, you see, I'm in home office. Maybe the internet is not the best.
It's just a stress intensity test.
Okay, yeah, it's a stress intensity for me now. But I'm pretty glad that you still hear me. Would be worse if this doesn't work as well. Okay. Okay, so here we are again. I sent it to you, Sherry, but I will try to go on here first.
Okay, I'll look out for it.
Okay. Yeah, the next thing I looked at, okay, finding back the red path, I think is I looked at the solids concentration. And as you can see here, can you see my mouse when I move it?
Yes.
Yes?
Yes.
Okay, then
Yeah.
I'm not using the pointer. Maybe it's easier to do it like this. Then I looked at the solids concentration, and as you can see here in the first graph, it's in principle the origin stress model run with experiments for different solids concentration from 5 to 50%. And what at least is happening here is that if you run these experiments, you get for each concentration at least a certain medium particle size for a certain specific energy. This can be seen here in the gray boxes. And at least we have to summarize here that if we want to use the origin stress model, we need at least for each concentration a separate curve. So it's not possible to do it here with the original model because at least the concentration is not recognized at all. With this in mind, I calculated at least the theoretically caught particles between two colliding grinding beads. And here you can see pretty well the different influences with regard to the parameters we need inside our model. On the one hand side, you can see here on the x-axis, the medium particle size, which is at least decreasing or increasing depending on the side you look at. And you can see that with decreasing particle size, the number of caught particles increases. On the other hand side, for the smaller grinding beads, here the circles, the concentration was varied in a range between 0.1 and 0.3. And what you can see here, the curve in the middle is 0.2 as solids concentration, and the data points below are 0.1, and the ones above the curve are 0.3. And you can see how big the influence on the theoretically caught particles is when you increase the solids concentration. On the other hand side, for 0.2, I changed the grinding media diameter as well. And when you compare the black data points here with the circle where the small error is at, you can see that the influence is not that big. But at least all these three parameters have to be included into the model. And I realized it in the way that I took at least this calculation for the theoretically caught particles, skipped off all the constant values you see like P and so on when you calculate volumes of spheres, and put in the values which were interesting for us into these stress intensity. And these are the grinding media diameter, the product particles sized to the square, and the solids concentration. And still you see here at least the energy transfer coefficient of the product. And so I thought, okay, with the stress intensity, I created a value which is more or less reflecting something like the energy which is transferred to the product. And now on the other hand side, I need at least some material parameters which are reflecting somehow the breakage energy. And when you look at steered media milling processes, well, they are filled up nearly 70 to 90% with grinding beads. And so I thought, okay, the main stress mechanism in such a mill will be compression or shearing. And so I looked up which parameter is sufficient to take this into account. And then I looked up for compression strength of the different materials I used. And so at least you have to see it's something like a material value, but for, let's say, the basic material itself. As we know from the literature, the particle size itself will also play a role, because with decreasing particle size, the resistance against breakage is increasing. And at least each material has a certain physical grinding boundary, which means at least at some stage of grinding, the particles get that small that they are not able to store anymore some energy. And so they are not able to break anymore. And so I took up these 3 parameters and put it together in one, let's say, material specific value describing the specific energy which is necessary for breaking. So I took this compression strength and something like, I said, a dimensionless particle size, which is at least taking into account the grinding boundary and the current status of my particles. And then when I looked this up, I correlated the optimum stress intensity values I get from the origin stress model with this material parameter for different materials and also different mills for my nanogrinding experiments I did. And then all these data points here were at least achieved. And as you can see, there is a correlation between both of them. So I said, okay, with this model, it seems to be possible, if you know your your material parameters, to estimate here the optimum stress energy. Later on, we had this 2 master thesis with the dolomite grinding. And I said, okay, I have a look at the data, not so many experiments, but I found some optimum values, which were here, just to prove if it's possible to extend at least this model to coarser particles. Because here we ground the particles, let's say in the tens to 1s micrometer range. And here, these are really all particles below 1 micron. So it seems to work. Now, if we go on, we can say, okay, so each data point you see here is connected to at least minimum 3 experiments, because we have to find experimentally the optimum. But at least when we say it's a general function, we can see here, it is not necessary to do it for all the materials again and again. You can use this curve. Okay, then you might say, okay, I don't know the grinding limit of my material. It's true, it's hard to achieve it. For some materials, we ground as far as nothing happens anymore. But to be honest, for silicon carbide, for example, we didn't do this because the wear of the grinding beads was even higher than the grinding success at the end. There we used another way, which was shown by Knieke first. She said, okay, the grinding limit is correlated with the crystallinity or the crystalline structure of the material. And so it was able to calculate it. And this was realized here for most of the materials. And if you now compare at least the compression strength with the grinding limit of the material, you can roughly see a dependency of both of them. So if you say, okay, the compression strength I can find somewhere in the literature or in the internet, it's okay, we can estimate the grinding limit out of it because it's connected. And now what we can do with it, well, we can calculate our optimum parameters. As you have seen in the curves before, there were no results included for the discus geometry I showed you at the beginning. And now we had this industrial project where we got this discus geometry for our mill. And I said, okay, let's see what's happening if we grind material like silica. This was at least the thing the company would like to have. And so calculated at least the F-mill factor from the geometry. As I said before, we had a silica. We know probably the parameters because silica was a material I used for my nanogrinding experiments as well. And let's say we want to have a particle size of 2 microns. then we can calculate out of the material parameter, which is like this, and go on with my curve and see where the optimum stress intensity is located. You can do it directly by the graphic. I have a fit function for it and use it, and so I get a very clear value for the stress intensity. And now with this value, you can at least fix your parameters you would like to have, like let's say the solids content you would like to have, the grinding media you have available, the filling ratio, and so on. And in our case, we had 3 different grinding media sizes available, which are shown here. The smallest one was around 1.5 millimeter, and the biggest one was around 2.65 millimeter, and one in between. And if you now rearrange at least your equation for the stress intensity to the stirrer tip speed, because it's the last parameter we haven't chosen, we can calculate at least optimum values for these 3 grinding media types, which were for the smallest one around 7 meter per second, then 4.6 for the medium one, and 3.8 meter per second for the biggest ones. And then we looked at the grinding experiments, and this was the result. So at least we have here a typical, let's say, plot, the medium particle size over the specific energy. And we ran the experiments usually with 9 meters per second. So you see here the different grinding media types for 9 meters per second, where at least the smallest ones were already the best. And then we said, okay, we run one with a even smaller stirrer tip speed, and we see that the curve is just shifting a little bit, but at least it's pretty clear the smallest grinding beads are here the most efficient ones. Okay, so this seems to work very well. Now I went on and thought, okay, would be really nice if it's somehow possible to find out about the grinding time or even the energy which is needed to run the process to achieve the particle size. Therefore, I thought about the different energy dissipations and how the specific energy is connected at least with our, let's say, numbers like the stress number and the stress energy. And this equation was already shown by Quade and before. And what we see is at least that we have a certain specific energy which is given to the process, and we have a lot of energy dissipation inside our process due to, for example, friction of the grinding beads at the grinding chamber walls or beneath each other. We thought about the energy dissipation into the suspension. I already talked about this. Then there was the idea of grinding media contacts without product, but I think we can neglect it because for fine products and higher concentrations, we see that you have always product in between and the deformation behavior, and at least you came up with this. These two, the energy transfer coefficients of the suspension and the product, were already included or neglected. And before I would like to tell you something about this energy transfer coefficient of the mill, I would like to first talk about the stress number itself. Because at least in the first part where we predicted at least optimum process parameters, we had the main view on the stress energy. And when we want to come up at least with the grinding time or the energy, we need also an idea how to find the stress number for it. And therefore I thought, okay, in general, I think I would need 2 different grinding or stress numbers. On the one hand side, I have a stress number of the mill. This is at least the number of grinding media context which is delivered by the mill during my grinding time. And so you can see here the revolution number of the stirrer. Instead of using the grinding media contacts, which we for sure don't know, we introduced here the number of the grinding media, and we have got the grinding time. You can express the number of the grinding media by their mass and their size and density, for example, but also by their filling ratio. On the other hand side, I thought, okay, we also need a stress number which is somehow correlated to the product, something like a product-related stress number. Because on the one hand side, the product is not maybe breaking at each contact, then you have got many particles or several particles within one stress event. And at least the product is maybe not the whole time in the mill, because you run your process, for example, in a circuit mode or in a passage mode or whatever. So at least the grinding time is not necessarily the same time as the product is in your mill. And so I, let's say, widen the equation a little bit. In the basic, it's the same. It's the amount of grinding media inside and the revolution number of the stirrer. But instead of the grinding time, I introduced here the residence time. I introduced also a term which is at least here, let's say, representing how much material is in your system. And all the values you will see in the future, they are always related to the volume of your product, to neglect at least the influence of the density. So as you know, the same solids mass weighted by mass might be different for different products as the density might change. And then I had this value where I compared at least the distance between the optimum stress intensity and the stress intensity which I adopted at my mill, because maybe it's not possible to use the optimum one, or not desired at least. And here this alpha value is also something like a material parameter which is reflecting the fracture behavior at non-optimum conditions. Maybe to make it a little bit more clear, I would like to come back to the first figure I showed you. This alpha value reflects at least the slope of the curve at the right and the left-hand side of the optimum. Because the thought was, at least if you go to the left-hand side of the optimum, you will need multiple stressing events to make a fracture possible, because the transferred energy is too low to break the particles at even one stress event. And if you go to higher values, well, you will have more fracture pieces by giving more energy to it. And this has to be reflected somehow as well. But at least it's not going to be more efficient. Also, you have maybe more fracture pieces afterwards. You will also have a lot of excessive energy for wear, and which is dissipated into heat. So here at the optimum stress energy, one fracture event should occur to one stress event to have two pieces afterwards. So this is the model idea behind this. And then here I took the optimum stress intensity and took it into relation to the product of the stress intensity, the optimum one, and the product related stress number. And this is the result here. You can see it for the nano grinding experiments, and here below for the different isomill experiments. And when you look from the distance to this curve, you'd say, oh, pretty nice correlation. Yes, it's a good correlation, but when you look a little bit more in detail, you can see, especially for the small mill and the nano applications, the deviation is pretty high. So the deviation is about 2 to 3 decades, and I would say, okay, it's somehow describing what is happening there, but at this point of view, I have to say, okay, we should be a little bit careful to say, oh yes, it's the best thing to do to recalculate the grinding time. Nevertheless, you can do it for sure, and you can see that especially the scattering for the bigger mills is much lower. And my advice here would be, okay, I can show you how to do it, but you should know the mill you would like to look at. You don't do this for a mill you never used before at this kind of stage to back calculate it, because at least if you take a value which is I will show you later on, which is not in a good range for your mill you would like to use, you can have a totally wrong time. But let's see how we can generally do it. Also here, I put a fin inside, and then I took the parameters from the discus mill we saw before with the 9 meter and the 1.5 millimeter. And we have here the optimum stress intensity we calculated before from the other master curve. For these parameters, the stress intensity, well, it's by a factor of 10, roughly higher than the optimum one. We know the alpha value because we did some quartz grinding before. And here we have the total mass in our system and the density out of it. And then at least for sure, you have all the parameters you would like to have. You can look at this curve and you can see here that you can find a number between the 22nd and 23rd power, but it's pretty hard to see. And with the fit function, it's a little bit easier. And when you recalculate it here, I came up with a residence time of 415 seconds, which can then be calculated to the grinding time. In this case, we run the mill in a circuit mode. And in circuit mode, the residence time is connected with the grinding time. As you can see it here by the grinding chamber volume, the volume of the grinding bead filling, and the volume of the suspension itself. And then we came up with a grinding time of roughly 1,500 seconds. And when you compare it to the results here, you can see, okay, it seems to work pretty well. Yes, because I know this mill and I had the one or the other experiment available to look and prove if this is true. But if you take, let's say, 1/10 more, you might came up with a grinding time of, let's say, 100 seconds or even 10,000 seconds. So here you need to be really show what you do. Okay, and then I would shortly come back to this diagram because there is one thing I still missing when we want to calculate the energy. And this is this mill energy transfer factor. Here I had certain ideas how to do it. My first idea was to run the mill only with the liquid phase and to see how the power consumption running the mill from the liquid phase with suspension changes, because I thought, okay, the suspension will play a role. At least I have to say this was not running. We tried it, but we saw very clearly that there was no connection which could be really found. So I thought, okay, when I need to run experiments without material and with material, and it's very far too complicated, I said, okay, I run experiments with, let's say, the material and different grinding media sizes, and then you can come up with these curves here, where you have at the x-axis the product of the mean stress energy of the grinding media and the stress number of the mill in relation to a volume-specific energy. The volume-specific energy is in principle the same definition as the mass-specific energy, only that I related it to the volume of the product and not the mass. And when you look at the curves, 3 different products here, they look different, but in principle, for all them, the same is that we see a dependency on the grinding media size. So with increasing grinding media size, the slope of the curves is decreasing. And I looked it up in the theta geometry for 7 different materials. And what I found is when you also compare here it the values for the slope for the different materials, they are all in the same range. They are not totally equal, but at least the factor before is always in the same size range, and the exponent factor is also always in the same size range. And so it was for the other materials. And then I decided, okay, I make a mean value out of it and take a general correlation for the slope of these curves, which is at least shown here. And when you do this, and I did it also for the other mills, at least this is the result. You can see that you have pretty good correlation if you introduce this mu factor here, which can be described by these power functions. When you look at the power functions, to be honest, I didn't see any correlation where I could say, okay, the size seems to influence it in this way and or in that way. I can't say, okay, there is some rule I can give you here at the moment. Maybe you have an idea how to do it, but for me it was not clear. But at least it works. If you can find, let's say, this correlation for your mill, you can back calculate it for your mill. And this I did here for the discus mill. This was at least the correlation for the energy transfer coefficient, and this was the time we estimated. You can estimate now by using the stress frequency, which is at least the stress number of the mill, by neglecting the grinding time, the power consumption of your mill, which was here about 590 watt. That's not so bad. If you look at the experiments itself, it's fluctuating this value. So the power consumption during the one experiment was fluctuating, I guess, between 550 and 660 watt. So this 590 is okay in this case. And with it, you can also calculate then the specific energy. And as you can see here, it's not exactly the value. I think nobody can expect this, but it's the right direction where the value is located. And if you're sure with it and know your mill, then you can now start playing and optimizing your mill in the way you would like to have. For example, here we have got the specific energy values for the different experiments we did. And you can compare here the calculated with the measured values. At least, sure, you see some deviations, but the dependencies were given in the right way. Or you can go further and calculate, for example, the throughputs. If you want to optimize your process with regard to the throughput, then you can see here at least that, okay, with increasing stirrer tip speed for the smaller grinding beads, the throughput is increasing. So the values show the right dependencies, but at least there are still some deviations. Oh, I'm sorry. And therewith, I would like to come up with my summary, what I can do and what I can't do with my model. At least what is possible is to introduce material and machine parameters to the model to calculate your optimum stress conditions. And I think this works really good. On the other hand, with the good knowledge and the second master curve, we were able to estimate at least the power consumption, the energy, the specific energy, or at least the time. And one thing I didn't show you before here is, maybe you mentioned, we have now several data points here. After running the discus experiments, I included these values here as well, just to show you that this idea with introducing the residence time instead of the grinding time to the stress number was a good one, because the correlation is very fine for the circuit mode as well as for the passage mode, which you can see here for the two blue data points. But at least these values scatter a lot, especially here above. So one has to be a little bit careful. And at least I would like to end up my presentation with the hint to say a mill isn't a mill, because a mill which is maybe located here in Braunschweig may have the same geometry as a mill which is located somewhere else in the world, but at least as long as the power measurement devices are not the same, or the temperature status of mill and environment, or the wear status, or even the material of rotor and stator will influence your results. So it's hard to say I can predict results for a mill, which is somewhere I never saw before. Yeah, and therewith, I would like to thank you for your attention, and I'm very sorry that the PowerPoint doesn't work. Now it does. Moreover, I would like to thank you here, Helmut Seeland, Arne Lüdecke, and Lukas Gerken, who were at least the ones who did most of the experiments we saw here, and at least Industrie Bitosi for making it possible to use their ISA mill in their lab. Okay, thank you.
Great, Sandra.
Yes. Excellent, Sandra. So I'm happy that it managed. Just when you send the email, the PowerPoint decided to
Yeah.
help you throughout the rest of the
Was the last
presentation.
chance for it.
Yes, indeed. Thanks for your effort there, and thanks for your fantastic presentation. And yes, I think we are a bit over time here, but I think we can.
Yeah, I'm pretty sorry. I think it was my fault or the fault of the internet. I don't know.
No worries. But I think we can take a few questions, but in the meantime, while people are thinking about the questions, let me just make one question, which is, yes, I think it is great effort from you, great really work to push forward the quadrant model there to make it more general. And I think it's really a great contribution. I was imagining that one part of the model that you push forward is the one that really deals with different materials, that you introduce breakage characteristics there. I see that you introduced the compressive strength and a correction for size there to account for the typical size scale effect. I was imagining that, of course, compressive strength most of the time, especially for ceramic materials, is very often hand in hand with Young's modulus, correct? Because the higher the compressive strength, typically the higher the compressive the Young's modulus. But in combination, most of the time we're looking at toughness rather than strength. So did you attempt to include the Young's modulus in that number there, and were not they successful? Because for minerals, sometimes this is kind of funny because sometimes a high strength has a low Young's modulus. Please go ahead.
No, I didn't try to do it right now. I can see at least that the Young's modulus is mainly influencing this alpha value. I showed you later on in the stress number, because this could be correlated very well with the Young's modulus. I think there is no clear correlation between the compression strength and the Young's modulus when I remember my values. But I think the compressive strength is correlated strongly with, now I don't know the English word. In German, it's the Biegefestigkeit.
Yeah, isn't it the toughness? It's the fracture toughness, isn't it? And like,
yeah,
the work.
So it's connected by a factor of 5 to 10. I saw in the literature.
Okay. All right, thank you. So, other questions from the audience?
I of course have some questions, but I'll ask you quite a simple one. In what is perceived in the industry is, when you have a stirred mill, they say it grinds by abrasion. It's an abrasion mill. And you put nice in your presentation, it's compression. All your material testing is compression. So what do I say to people, or you say to people, when they say a stirred mill is an abrasion device?
Yeah, I think abrasion and compression is not so far away, but it's a different grinding mechanism. I think when you talk about abrasion, you have very coarse particles and produce fine particles by keeping the coarse particle itself by abrasion. So this is my idea of it. And this is at least not the same mechanism as real fracturing it. I think then we have maybe to look for another definition of, let's say this model. And then I think it's pretty necessary to include the whole distribution. because then you will have a coarse part of particles and you will produce the finer ones, and you will always have a bimodal distribution.
Yeah, we get that very much in coarse milling because you've got big rocks and you braid the surface off. But it's a
as I said,
confusion.
I came from the nano area. For me,
Yeah, you came from the other side.
it was yeah, just nice to see that it works in the micrometer range. Maybe it's open to develop it even for bigger particles, and maybe we also have to change things here. I think it's not the end of the model. So that's why I said it's something like a journey. I started thinking about this, I guess, when I finished my PhD study somewhere in 2009, 2010. And then I always went step by step by step. And then I see, okay, some things work, some didn't. And here, this is at least the, let's say, the current status at the moment. And I think what is really missing is working, for example, with whole distributions. But still, I think then we have to talk about other methods like using, I don't know, a population balance, including into it and so on. Or the other way around, the ideas putting into population balances.
Yeah, people confuse the motion of the grinding media with the breakage mode. I think grinding media in a stirred mill is sliding, therefore it's abrasion. Well, it's abrasion on the grinding media, but not the particles. The particles is compression. And
the particles, the grinding beads are abrasive, yeah.
Yeah, I mean, they get compressed, so that I think it's such a misconception in the industry, and Marcelo knows this as well because he uses compression breakage. And so people think for stirred mills, you need some kind of mysterious abrasion test. You don't, you need a compression test. Anyway, it's an interesting side that it's absolutely predicted with the best models is from compression testing. So it's well justified. Yeah.
Other questions from the audience? It's a great opportunity to have.
As I said, I will come back to the ESCC and yeah.
Nice. Yeah, those who are there definitely can make additional questions in person.
Yeah, for me, it was pretty nice to do it today because I think I never talked about this, about time like 45 minutes and the whole thing. I always have some small parts up to now.
It is nice to present it all together. I agree. Yeah.
Absolutely. Well, I guess I think given the time constraints, and I think we can thank Sandra for the fantastic seminar here. Yes, a great treat for us who are interested across the board and comminution from very coarse to extremely fine. And I think stirred milling technology is definitely here to stay in the mineral processing industry. And of course, as you mentioned, in our chemical industry. So thanks a lot, Sandra, on behalf of the whole GCC. Great presentation there, and we're happy that you're a member, official member of the GCC. So we'll continue we hope to continue having your engagements with you now in your new position. Congratulations on that as well.
Congratulations, that's excellent. We'll follow you to Nuremberg, don't worry.
Yeah, yes, absolutely. We'll do that.
You're invited to come to Nuremberg and see up. I think Ulrich Teipel, who has the position before me, has a very nice lab, and at the moment I'm fighting for getting a stirred media mill there.
That's for sure.
To go on with the work, especially I have a project which started at the beginning of the year, which is about stirred media milling of slag materials, so which is maybe a little bit more nearer to ores than these pure materials. And yeah, let's see what's happening.
Excellent. Well, thanks a lot, Sandra. Yeah, please, Holger.
I think I was just recommending Sandra, just ask Arno, he has enough stirred media mills in Hanover, just take one with you.
Oh, indeed, definitely. That's one of the ideas. Well, so thanks, Sandra. Thanks everyone for attending this seminar. So next month, by the end again, we'll have another fantastic seminar to present to you from the GCC. So thanks a lot and have a great day.
Here. Thank
you,
you.
Sandra.
Have a
Thank you.
nice day.
Everyone, thanks, Sandra.
Bye-bye.
Thanks, everyone.
Bye-bye.